Hello everyone, today I am going to talk about the work achieving zero queuing delays for parallel jobs. My name is Wentao Weng, and I'm a senior undergraduate at Tsinghua University. This is a joint work with Weina Wang from CMU. Load balancing is a key part in today's data center because there are hundreds of millions of jobs submitted to the data center every day. And the data center has to balance the traffic load among thousands of servers. In the classical model of load balancing, there are in general a dispatcher and multiple servers. Indivisible jobs will arrive into the system in a random process, and what the dispatcher needs to do is to route one job to one server when it arrives. The goal is to minimize the job delay in data centers. So far, many load balancing algorithms with good performance have been designed, such as John the shortest queue, power of D, idle one first, and John the idle queue. Although they allow job delays to be small, these algorithms usually come with additional overhead. For example, John the shortest queue requires a lot of communication between the dispatcher and servers. For each arrival, John the shortest queue needs to query all n servers in order to find the one with the shortest queue. And for John the idle queue, it requires a memory of size n because it needs to remember which servers are empty. It then leads to a fundamental question. What is the trade-off between algorithm performance and its required overhead? Specifically, previous studies have focused on understanding this question by requiring algorithms to have the following property: zero queuing delays. It means that the average queuing delays converge to zero when the system size scales to infinity. It has been shown that when the traffic load is low, it's not quite heavy, John the shortest queue, John the idle queue, and idle one first can all achieve zero queuing delays. It also holds for power of D when the sample ratio D is at least log n over 1 minus lambda. Here lambda is a value between 0 and 1, measuring the traffic load in the system. However, there are also some impossibility results. First, for power of D, if the sample ratio D is less than 1 minus 104 minus lambda, then the queuing delay is non-negligible. A more general result shows that for a class of load balancing algorithm, achieving zero queuing delays require either the message rate is omega 1 or the memory size is omega log n. However, for today's data centers, many jobs can indeed be distributed computed. Examples include training machine learning models with massive datasets or doing Monte Carlo simulations. Specifically, imagine that the government wants to run 10,000 simulations in order to predict COVID-19. Then this big job can be decomposed into 4 independent subtasks, A, B, C, D here. Each means that running 2,500 simulations, and they can be run indeed in parallel. When all the 4 tasks complete by the computer, we can obtain the results for the big job by summarizing their results. Then to model such a parallel structure of jobs, we have to modify previous load balancing model in the following way. There are still a dispatcher and many servers, but now for a job arrival, it indeed contains multiple subtasks that can be run in parallel. In particular, in our paper, we assume that each job consists of exactly k tasks. Job will arrive into the system in a Poisson process of rate n times lambda over k. And the service time of tasks are independent and exponentially distributed with mean 1. It then implies that the traffic load of the system is lambda. For each job arrival, the dispatcher needs to design which servers this case of task will go. Note that the tasks can be routed to different servers because they can be run in parallel and they do not interfere with each other. For this new model, one interesting problem is thus, how should we design a load balancing algorithm such that job can achieve asymptotic zero queuing delays, just like that in classical model. Note that here we focus on job level delay rather than task level delay, because we want one single job to complete, not one single task. But before that, we first need to define what is zero queuing delays for job now, because each job may contain multiple subtasks, and it is non-trivial to define that. First, since each job completes when all of its subtasks complete, the delay of a job is exactly the maximum delays of its task. Then we first characterize the inherent size of a job, which is given by the job delay when there is no queuing for all of its tasks. The job size, or T star here, is indeed the maximum of K independently and exponentially distributed random variables of mean 1. As a result, the expected job size is given by 1 plus 1 over 2 until 1 over K, which is log K plus small o of log K. Based on this job size, we define that a load balancing algorithm can achieve job level queuing delays if the expected job delays only exist a negligible fraction of the expected job size when the number of servers goes to infinity. When this property satisfies, it simply means that the extra delay for job is so small and its response time is almost the same as its inherent job size. Based on this definition, in our work, we want to understand what the requirement on the algorithm's overhead in order to achieve zero job level queuing delays. The question is much different from previous studies because now the conditions of zero queuing delays differ significantly for indivisible jobs and parallel jobs. In this work, we also want to study whether the parallel structure of jobs can help us break through the impossibility result for indivisible jobs. That is, can we obtain zero queuing delays with a smaller message rate than the lower bound shown in the blue box? To answer the above question, we consider the following batch filling algorithm to load balance parallel jobs in data centers. In this algorithm, the dispatcher will sample KD servers per job arrival. That is, in average, D messages per task. Then the dispatcher will fill the task of this job to the empty spaces in the sample servers in a water filling manner. For instance, in this example, the dispatcher may sample server 1, 2, 3, and N. Then the 3 tasks of this job are routed to the empty spaces of server 2 and server 3 under the red line. What we want to study in this paper is how large the sample ratio D should be so that the batch filling algorithm can achieve asymptotic job level queuing delay. Our main results are as follows. We show that when the sample ratio D is at least 1 over minus lambda times log K, the job level queuing delay is asymptotically 0. In addition, we also show an impossibility result, claiming that the non-zero queuing delays happen when the sample ratio D is lower bounded by 1 over 1 minus lambda to the root of log K. Our result requires the traffic load is in the so-called subharmonic width regime, where the traffic load lambda is equal to 1 minus n to the minus alpha, with alpha to be a value strictly between 0 and 0.5. The significance of our result is that when jobs are indivisible, previous work shows that the sample ratio D needs to be at least 1/1 lambda in order to achieve zero queuing delays. But now we show that when jobs are parallel, the required overhead will be much smaller, given by 1/1 lambda times log k. In order to prove our result, the intuition is to understand when job level queuing delays can be negligible. Specifically, let us imagine that all k tasks are filled below a height h. Then we show that when h is small over log k, the expected job delay is upper bounded by log k plus small over log k. It implies that if all tasks of a job can be filled under a threshold h, with h equal to small over log k, then this job can have zero queuing delays. It thus leads us to think about for what state can batch filling fill all tasks under this particular threshold h. It turns out that we only need batch filling to sample k blank spaces under this threshold, as this greedy manner ensures that all tasks can be filled under this threshold and into these empty spaces. We find that indeed we only require the number of total blanks in the system to be at least n times h times 1 minus lambda. In this case, batch filling can be successful with a very high probability when we pick the specific clip D below. Here, the term 1 minus lambda is motivated from the fact that the fraction of empty queues is approximately n times 1 minus lambda. Then when we take D to be 1/1 minus lambda times h, we can see that the expected amount of sampled empty spaces is about k times D times h times 1 minus lambda, which is now greater than k. So there are enough sampled blank spaces for batch filling. So now it remains to show that the system will stay in a good state with a very high probability, where the total number of blank spaces is at least n times h times 1 minus lambda. We indeed utilize a state space collapse result. It shows that with high probability, either the purple region in the figure or the yellow region will be small. Note that the two regions is separated by the threshold h minus 1. The implication is that when the purple region is small, there are indeed many spaces under threshold h, because this number is at least n times the area of the purple region. On the other hand, when the yellow region is small, then the system is having a lot of busy queues. So there is no issue of no balancing, and tasks can depart system very fast. And in this case, the job level delay will also be small. We utilize Stein's method and Lyapunov-Gibbs method to make this argument rigorous. And combining all the above arguments, we can complete a proof for our upper bound result. And for our impossibility result, the intuition is to show that when D is small, there are many long queues in the system because of the unbalanced dispatch of batch filling. To simplify the analysis a bit, let us consider h is equal to 2. And we want to show that when D is small, there are many queues of length at least 2. Our proof utilizes the fact that the expected number of busy queues in the system is given by n times lambda because of work conservation. Then we only need to prove that the number of length 1 queue is small, which implies that many queues are of length at least 2. What we do is to use drift analysis on the Lyapunov function Vs equals to the number of busy queues in the system. The drift of this function is given by the number of sampled empty queues by batch filling, minus the number of length 1 queue. Now, since D is so small, we can imagine that batch filling cannot sample many empty queues. In addition, we know that the expectation of Vs is large, so its drift has to be large too. It then implies that the number of length 1Q to be small. So this procedure is kind of a proof by contradiction procedure. We utilize the fact that the expectation of Vs is large to imply that the number of length 1Q in the system is small. The above analysis can be extended to a larger H by doing induction. Please refer to our paper for details on how we do induction and how we design specifically Lyapunov function to prove for a higher H. And finally, combine all these results, we could have the impossibility result claimed before. So to conclude our work, we show that when jobs can be parallel, the required overhead to achieve 0 job level queuing delay is smaller than that when jobs are indivisible. However, the upper bound and lower bound in our work do not match with each other indeed, and they only work for batch filling. It does a future work to obtain tighter bound and see whether other load balancing algorithms can achieve a better trade-off between delayed and overhead. Thank you so much for listening. Hope you be safe and enjoy the conference so much. Thank you.